Hi, I'm Dino. We work on Pinot at LinkedIn. Well, Sabrina's now at Netflix, but she was at LinkedIn. How many people know what Pinot is? Ever heard of Pinot? Used Pinot? One person. OK, cool. Wow.
I used to work at LinkedIn.
Oh, hi. Maybe we met. That's cool. All right, so before we get started, I'm just going to give everyone like a super brief overview. Pinot is this OLAP distributed data store. Ever heard of OLAP? Show of hands, maybe? Yes, a few people. OK. Online analytics processing. So this is kind of slicing, dicing data. We're talking terabytes, tens of terabytes, hundreds of terabytes, not quite at the level of like Spark SQL, but kind of serving online systems. So we have this broker routing layer, set of serving layers that host nodes, and we push down SQL queries to process large amounts of data. This talk is going to focus almost entirely on the serving node aspect. So we won't focus too much on the brokers or anything else in this picture, but good to have an idea. Pinot powers a lot of different use cases at LinkedIn. Okay, we get a little peek under the covers. For instance, this member-facing analytics, who viewed your profile. We have enterprise-level products like this talent intelligence ecosystem that shows how talent is moving across the country. And then we have internal tools, business insights, this kind of thing. And each of these three use cases has kind of different query patterns with different latency expectations. When you open this LinkedIn.com, who viewed my profile, you expect it to be pretty quick, hopefully. But maybe internal analytics is more expensive queries, running on more data, and kind of has more relaxed latency profile. So with OLAP, unlike a lot of SQL products, the cost per query can vary really dramatically. Like you can have some queries super cheap. Other queries are unbelievably expensive. So just for a sense of scale, so we know where we're talking hundreds of thousands of QPS, tens of thousands of serving nodes, a couple thousand broker nodes, 5,000 Pinot tables. These numbers are a little old, but it works. So what we found is that originally, Pinot was deployed on kind of this general purpose app node at LinkedIn. OK, we have one size of host, and that's what we used. It was available. Eventually, we added SSDs to say, OK, SSDs are fast. Previously, they were a little expensive, so we had, OK, non-SSDs and SSDs. But as time passed, we have this question of, hey, we need different types of use cases. We have these CPU-bound use cases. Maybe they want to process more aggregations. Maybe they do more CPU-bound work. Maybe the whole data set fits in memory. We also have these memory-bound use cases that really rely on memory to compute like a distinct set. And we have storage-bound use cases. OK, we have I/O throughput-bound use cases, and just raw physical storage-bound use cases, these internal business analytics. Generally, the data just sits at rest. So it didn't make sense to keep going with this one SKU to rule the world. And use cases that didn't really quite match kind of wasted a ton of hardware. So if you need a lot of disk, your CPU is kind of just sitting idle. So that's our goal. Figure out, A, how to support multiple SKUs without creating a whole bunch of toil. How do we integrate them into the ecosystem, and how do we manage this fleet of hosts? And we justified it, as all things do, by saying that it's going to save a lot of money. Okay, and so our goal was kind of 20% rough estimate because we had to keep using the hosts that we have. We already own these hardware. Can't really throw them off the window. So we said, okay, 20% seems pretty reasonable. And we'll talk about how we did at the end. The other justification that we have found, historically speaking, is the larger the host, the more cores, the more memory you put in it, the cheaper it actually is. So keep that in mind. It's not super important for this talk, but you'll see. We can't kind of really give exact numbers, but we'll speak in vagueness. All right, so goals, 20%. We really wanted to support any arbitrary SKU eventually. So we know year from now, different hardware is going to be cheaper, different hardware is going to be available. It'd be good to be able to add it. We wanted it to not create impact as we move these tables and tenants between hardware. So if we migrated this who viewed my profile and it causes a bunch of latency spikes, people will be unhappy. So we didn't want to do that. And we really wanted to automate the whole process so we're not injecting a bunch of toil. And as we scale with SKUs, we have to scale with people. That doesn't really work out. So prime directive, minimize the additional work per SKU. That being said, we did find that there's other non-automatable parts to adding SKUs. Okay, you have to order hardware. You have to manage the spare pool of hosts and SKUs. So there's this trade-off between, okay, we're going to add additional SKUs and support them, and we want to minimize the cost. Yes. Good. And our non-goals. Okay, we don't really want to improve the utilization per host. We just want to save money. If we accomplish the goal of saving 20%, we're happy, even if the utilization may still be low. Good. Okay. Nice. So we have a few pieces to this that we ended up building. We have kind of this orchestrator, which is managing the whole thing. We have some production metrics and storage to gather a little bit more deep metrics about how the hosts are performing. All this gets fed into this cost estimator and SKU recommendation engine, which kind of knows what SKUs we support and what their hardware is. And then finally, we have this migrator, which takes a tenant and tables running in production and moves them to from one SKU to the other with no impact. And Ja is going to talk about all of that. Thanks.
Okay, folks, so before we get into the design details, like technical part, let's think about, like, at a high level, if we're going to do this problem, how are we going to approach it? So basically, we are trying to build a new cluster for an existing cluster that will use some new SKUs, will apply some new dimensions for the cluster so that we can make it cost efficient. So there are two questions we basically need to answer here. The first one is we need to have a set of metrics defined and methodologically collected to basically profile the utilization of the resources on the old cluster, right? And on top of this profiling, we're going to build some heuristics, some model to map this utilization to some new SKUs and new dimensions so that it's going to be, like, cost optimal. Okay, so to answer the first question, we basically want to collect the metrics, like we collected the metrics in 3 dimensions: CPU, memory, and storage. Okay, so for CPU, what we did was essentially we took a look at the total number of CPU cores on a given cluster serving a use case. And we want to scale down the number of cores if it has some utilization below a threshold. So here we take that threshold as 60%, meaning that if the total CPU utilization is below 60%, we're going to scale down the number of cores so that we get some reasonable utilization rate while we still leave this 40% of the headroom for the organic growth. Here we do not really count the stuff like CPU frequency, IPC. These things are too kind of nuanced. But if we're gonna develop this model to have more fine-grained prediction, we'll probably account for that in the future. So with that being said, after we scale down the number of cores, we still want the cluster to withstand 99.99% of the traffic, so that we serve you well while you are scrolling through feed, while you are trying to do job search. Okay, so to do that, because Pinot runs query in a very low latency, tens of milliseconds, we need to really collect the CPU utilization things in a very frequent manner. We do that every 15 milliseconds. But we still don't want that to impact our system application performance. So we did some research and found that this Linux performance copilot is really useful, and it really offers low overhead metrics collection, publishing, this kind of stuff. Okay, so the story for memory is a little different. So Pinot's memory usage is composed of three parts. The first one is the Java heap memory, which is managed by Java memory allocation, the GC algorithm. And the second is the off-heap buffers, which is basically the buffers we allocate using some Java buffer libraries, and we kind of manage them manually within our program. And the third part is Linux page cache, which essentially we use mmap to kind of map these data shards from our disk to the memory, and we read them from this mmap. So the mmap will be managed by Linux system, and it will basically appear as Linux page cache. Okay, so the green and the blue box here, if we sum them up, it will be reflected as the RSS memory, which we collect, and we put a headroom of 1.5 on top of it as the final memory usage. As for the memory mapping part, this part is a little tricky, whereas in the first version, we actually tried to figure it out, but due to the kind of lazy eviction of these pages, you don't really know which pages are really used, which are not. So we kind of use this factor on the RSS memory to give some headroom as well for the memory map section. Okay, so the storage side has a flavor on both sides, I would say. First, you will need to have, in steady rate, some storage capacity allocated on those hosts, so that they are enough, to hold all the segments in the disk. And I guess what's more tricky here is that when you actually start to use these segments or the data shards, when you mmap them into the memory, when you start to read, they will be loading to page cache, and this process is paging. So although we're using like really high performance NVMe SSDs, the process of paging is still kind of bounded by the SSD speed, namely the throughput and the IOPS. Therefore, in this practice, we want to capture the the throughput, IOPS, kind of like how we capture CPU. We want to capture all the bursting patterns so that we make sure when we upload new segments, when we are downloading new segments to the server while we are serving queries, there's no thrashing, there's no conflict, and the bandwidth is basically enough for both operations. To do this, we also use this PCP to capture the sub-second granularity of IOPS and throughput for the NVMe SSD. Okay, so to make this process really automated, we built this nice workflow around the Pinot ecosystem. So I guess the really challenging part here is that because we're collecting the metrics in very high frequency, 50 milliseconds, and we have so large of a fleet size, the data itself can be very large. So the optimization we've done here is that instead of really storing all the time series data, what we really need here is just the percentiles, right? So we shift ourselves and look at the data in a view of distribution. And to do that, we basically leverage this T-digest algorithm, which in a fixed time window, let's just say 1 hour. After we've collected 1 hour of CPU utilization on the server with a frequency of 50 milliseconds, we kind of look at all this data and we draw the distribution for it. And then the algorithm will basically take maybe 1,000, 10,000 data points as the representative points of the distribution itself. So this is some lossy compression of the distribution, but we did enough experiment on this, and we picked the these parameters really carefully so that the margin of error is really small. So yeah, on each host, we will basically do the PCP collection, and for a fixed time window, it will turn them into these T-digest points. And these T-digest points will be kind of serialized in bytes, and we will publish them to the Kafka topic. And eventually, it will get ingested to Pinot table. And we use this compressed kind of view of the distribution to do the recommendation, which is what we used previously for all this percentile stuff. So the good thing about this T-digest is that we can actually query them and merge this T-digest on the fly, within Pinot. So Pinot has this percentile T-digest function, which it will basically take some column of T-digest, raw T-digest byte data, and given a time window, given some filter, for example, if you want to look at the percentile of CPU utilization of past X days or a given cluster, you can write a Pinot query on the fly. And you can put any number for the percentile there. You can put 99.99, you can put 3 nines, 4 nines. It will give you a really accurate estimation of the percentile data on, for example, CPU metrics. Okay, so this largely kind of reduced our storage for these like metrics data for different dimensions and for such a large fleet size. And the data management, ingestion, like the data kind of boundary and the query, we all like implement those in Pinot. Okay, so on top of this like rich metrics data for the clusters, like this utilization data, the heuristics to actually come up with the best SKU and the size for a given cluster is kind of like straightforward. So as you can see here, let's imagine you have a large list of SKUs, and each SKU has its own number of cores, has its own like RAM size, and you can attach some number of disks to it. And each disk has its own size, IOPS, and throughput. So these are the capacity for the hardware. And what we do here is basically you will say, for this cluster, I want to provision X number of such SKUs and Y number of disks, so that the disks are kind of evenly mounted to all these machines. And for each host, we will take some number of cores out of like the host, basically for some OS operations. And we also keep some RAM buffer for the operating system, for the daemon as well. So after that, we will make sure that the capacity, like all the capacity are on the left side, like in the right font. The total capacity of the cluster will need to be larger than those like actual resource usage of to serve the table. The resource usage is basically these percentile numbers we measured on the real cluster. So now this problem becomes really a like linear programming problem, where we try to minimize the total cost of using such SKUs and disks, while we are still trying to satisfy all the capacity need to serve some percentile of like traffic. Okay, now I'll give it to Sabrina.
Yeah, so Jia just went over how the capacity estimator and the SKU selection algorithm works. And then the next step will just be taking the output that's the target SKU, and how do we migrate existing SKUs and then also provision new tables. So the first one is we want to do the SKU migration in a impact-free manner. That means our end users should not notice any downtime, or their performance should not experience any degradation. And then the way that we do this, the key point here is to provision the new SKU and then running the cluster on both of the new SKU and the old SKU at the same time. So essentially their cluster is under double the capacity. So the way we do this is we first allocate the new host on the target SKU, and then we will add the table and the tenant to the new SKU, and then also tag the new host as well. So at this point, the table will be running at double the capacity. And then at the routing layer, that means roughly 50% of the traffic will go to the old SKU, and then the other 50% will go to the new SKU. And then we will go into a round of evaluation. So in the evaluation, we will look at the query performance, the P95, and then we will also look at other metrics such as memory usage and CPU utilization just to see if everything looks good. If everything looks within expectation, then we will go into the disable old replica stage. Here, what we do is to do a soft disable on the old host. So we're actually not removing any data. We're just disabling it at the routing layer. So that means queries will not go to the old SKU after this step. So that means 100% of the load will now go into our new cluster on this running on this target SKU. And then we will enter another round of evaluation. That means we'll look at the same performance metrics again to see if everything makes sense now that we have 100% of the traffic. If everything looks good, then we actually wrap up the whole evaluation system, and then we go into cleaning up the old host. So after this step, everything will be running on the new SKU with no performance impact. And if any of the performance evaluation loop go into a bad state, that means if we see query performing worse, then we will immediately enable the old host. So this is very quick to do. There's roughly minimal impact. And then we will automatically roll back, and then we'll also alert our engineering team to take a look to investigate. So this is how we do the SKU migration with no downtime. And then after migrating existing tables, we also want to look at how we provision new tables, taking in consideration of the new SKUs. So at Pinot, we have this Spark provisioning system. This exists like long before we have this SKU migration project. It's a really smart system that takes user-provided inputs, such as table characteristics that can be the column cardinality, the schema, and the QPS that they want, the query patterns that they have. And then we'll also take in like latency, SLAs, storage requirement, and then we'll translate this into what is the capacity needed to provision their table, and we'll automatically do that. And then there's two steps that's in the process. One is the first provisioning step, where we are provisioning the new cluster, and then they can start ramping their QPS. And then the second step is we will go into a ramp evaluation loop that will look at the table at the lower ramp, and it will extrapolate how much capacity that we need if they enter the full ramp phase. And then we will also determine if uplift will be needed. And then both of these steps, we made a SKU aware. That means for the first step, we will pick the best initial SKU with the lowest cost that can serve their production queries. And then in the second feedback loop, we will also consider multiple SKUs as well, so that this process can be SKU aware, and it will evaluate based on the SKU that's currently in the cluster. And then lastly, once the table enters a steady state in production, that means they're fully ramped, customers is using it as usual. And then after some time, they will come back to us and ask, can we ramp more QPS, or can we increase the data retention? Essentially, they want more capacity. And then we also have this headroom estimation system that will look at the headroom of their existing cluster and see if we can support more QPS with the given cluster size. And then in this process, we also add SKU intelligence to it as well, so that this evaluation can take into consideration of like the memory size, the disk size that's available in the cluster as well. So we did all these three things so that our existing smart provisioning system works with multi-SKU. And then lastly, to make things even better, we actually have a very convenient benchmarking tool that's available for both our team and our customers' team to use. So the purpose of the benchmarking tool is they can spin up a production-like cluster and then run real queries with real QPS, and then we can test out if the cluster can support such use cases. And then in this benchmarking service, we also offered SKU selection as well. So in addition to ramp their QPS and query pattern, we also made a self-serve so that they can select the servers that they want, the capacity that they need. We give them a pool of SKUs that they can use, also for us, for validating during the process as well. And then in this process, they're able to test out real queries on multiple SKUs. So lastly, we had some very impressive results. We meet our goal by reducing the total cost to serve by 35% by migrating only 20% of the clusters to the mixed SKU. We also reduced our overall cost of future hardware forecast by 57% last year. And then as more SKUs come in our spare pool, we can easily support adding more use cases and onboarding new customers very easily with the smart provisioning process. Okay, lastly, we just want to express that this project takes more than just the three of us. There's also a larger team who's not with us today. There's Florence, Sonam, Shirayu, and Siddharth that we want to say thanks. Yeah. Okay, cool. questions.